Uh, the next topic we need to talk about is how we estimate the slope. So even if even if you see a line on this graph, but actually you do not observe a line from the data. So what you have is those points. So you have those points and you need to draw a line by yourself. So that's estimation, and we are going to discuss how we can do it. Let me review the least squares idea. So the starting point is a prediction problem. Suppose that you would like to predict a variable y using by a predictor m. So say for example, when you throw a dice, I have to guess what would be the outcome. So I may say it will be 3 or it will be 4. So there may be prediction errors, but I would like to do the best prediction possible. So let's think about that. I have to say one number to predict a dice outcome. So suppose that you observe you repeat the experiment many times, and from those observations, you can define the prediction errors as the difference between each observation, the distance between the observation and your predictor. So suppose that I predicted dice will be giving 3, the outcome will be 3, and if the dice outcome was 6, then prediction error is plus 3. If the outcome was 1, then the prediction error was minus 2, something like that. So if you observe 100 observations, for example, then there will be 100 prediction errors. Some may be correct. So if your prediction was perfect, the error will be 0, but it cannot be 0 always. So some will be negative, some will be positive. So positive errors imply you are overestimating, and or others. Excuse me, I changed it. So when the prediction error is a positive, it means you are underestimating, and negative, then it's overestimating. Anyhow, it's my mistake. So anyhow, point is some are positive and some are negative. And what we want here is to measure the size of the prediction error. How much you have, how much error you have in your predictor. So then the simplest way is to sum those prediction errors. But the problem is, if you simply sum all these prediction errors, the positive errors and negative errors will be cancelled out. So in the end, your errors, you cannot measure the error at all. So therefore, to prevent those kind of offsetting by positive and negative errors, we take squares. So squares, taking square makes everything positive. So after taking squares, sum those errors. So square, and sum up all the guys, and then you get the sum of squared errors, which is our measure. We are going to use it as the measure of the amount of prediction errors. The total prediction error is measured by sum of squared errors. There are different methods to measure the size of the error, but this is the standard and the most commonly used measure. So let's just focus on this measure for a while. Anyhow, in a previous lecture, I introduced this idea at the exactly same way, and as a result, we would like to minimize this error. So the sum of the squared error is minimized when the predictor equals the mean. So if the predictor equals the sample mean, you can minimize those sum of squared errors. That was an argument, and that's an argument that the sample mean is the best estimator in that sense. So we are going to extend this idea to the regression model. In the regression model now, the difference is the same thing is that we are still predicting y, but the difference is that we have an additional information in x. So previously we would like to predict test score without knowing anything. So just choose any school and you have to predict the school's test score. But now you have additional information in the student-teacher ratio. So using that information, you have to predict. And the regression model, by the regression model, you can set up the predictor in this way. Given the student-teacher ratio you observe, you can predict y using beta 0 and beta 1. So it is you are choosing two numbers to predict y. That's the presence of additional regressor. And then from the same repeated observations, you can define a prediction error from that observation this way. The actual outcome, y is the actual test score, and this is your prediction. Beta 0 plus beta 1x is your prediction. So their difference is the prediction error occurs for the ith observation. So, and in the same way, these prediction errors are summed, are squared and then summed. So the measure of the amount of prediction errors in your predictor is the sum of squared errors in this form. So the idea is the same. The actual observation, realization, true realization, and your prediction. So their difference is the error, and error is squared and then summed. So sum of squared errors. This is this is the amount of prediction error you are making. And what we would like to do here is we would like to minimize this. We would like to minimize the prediction error. So that's what we are going to do. How? So then this is just mathematical derivation. Then we are in practice we are going the other way. We start from this sum of squared errors. We would like to minimize this, and by minimize this by choosing beta 0 and beta 1 more carefully. So you can write that in this way. Without regressor, you minimize sum of squared errors by choosing m carefully, choosing one number m carefully, and we know that the answer, the minimizer, is the sample average y bar. And if you extend, by the way, how can we how can we get the sample average? The idea is the minimization problem, and you derive its first order condition and make the derivative. So its derivative with respect to m should equal to 0. So if you solve that equation for m, then you are going to get the sample average. But anyhow, the result is quite intuitive. And you can extend this idea to the regression model. So now you are minimizing the sum of squared errors. This is the sum of squared errors, and minimize this guy by choosing intercept and slope carefully. So minimize with respect to B0 and B1. And the results, the minimizers, the optimizer, the minimizer, the outcome, the solution to this minimization problem is called the OLS estimator, ordinary least squares estimator. So the least squares means that squared sum is minimized, so it is called least squares. And we put ordinary least squares because later there are variations of this method, so they are called like generalized least squares or like two-stage least squares. There are many variations of least squares methods. So we just to show that this is the just simple basic least squares methods, we call this OLS, ordinary least squares. So ordinary least squares estimator solves, minimizes the sum of squared errors. Also, its derivation, the solution, it's not that difficult actually to solve for the B0 and B1, because you can just differentiate and obtain the first order condition and solve for B0 and B1. It's a little bit cumbersome, but not difficult at all. But I'm not going to show you here. Or that's basically, so this is, now go back to the data. From this data, we are looking for the slope. What is the slope, right? So in our data, there are more than 400 observations. This is the real data provided by the textbook. And this is how they look. And using the sum of squared ideas, minimization will be you can minimize these guys to obtain the result, to obtain the OLS estimators using the values from the data. And then the calculus is not important, I believe, here. So the result is more complicated anyhow. The beta 1, the slope, looks like this. Slope looks like this, and you don't need to memorize this slope, but maybe it is more intuitive. S of x, y, the numerator is the covariance between x and y, and denominator is the variance of x. So the numerator, the covariance, captures the relationship between x and y, which is closely related to the slope, because slope is basically the relationship between x and y. And you don't need to memorize this. And your exams will be take home. And if you want to see the formula, you can just open the slides. So I'm not asking you to memorize this idea, this formula. And also, when you need to calculate beta 0 and beta 1, the program, the software will do this. So you are not going to you apply this formula directly to the data. You may do, but you don't need to. There are softwares, built-in commands, so don't worry about that. And then, so anyhow, if you can calculate the covariance and if you can calculate the variance of x, then by simply taking their ratio, you get the slope. That is your estimator. And beta 0 is based on the sample mean of y and sample mean of x. So beta 0 is to match their sample means, sample averages. So you can calculate those, and after calculating those, you may predict y by y hat. Y hat is defined in this way. Simply, it's just plug simply the regression line with the estimated intercept and the estimated slope. So this is how you predict. So once you obtain beta 0 and beta 1, you are going to predict y this way. And after you predict y, you can calculate the prediction error. So y hat is your predictor, and y is the real slope, real outcome. Excuse me. So real outcome and your prediction. So their difference is your prediction error, and that will be denoted as error hat, u hat I. So error is also calculated, or residual, that is called as the residual. So so this looks a little bit complicated, but actually it's nothing. Covariance, variance, sample mean. So calculating beta 1 and beta 0 is quite easy. It's as easy as calculating covariance and variance. So computer can do it like instantaneously. So don't worry about the formula. And after you get these, you can manipulate the data and like predict y based on the estimates. Okay. Next, so this is how we estimate the regression model and how the softwares, so statistical softwares, will estimate the regression model from the data. So just I wanted to give you the basic idea and how the basic mechanism, how the calculation is justified. Okay, I'm going to resume in the next video. See you later.